All right, let's talk about continuity. So we have this little cheat sheet here. Let's talk about what even is continuity. Well, a function is continuous at x equals c, so any number, if the function exists at that number. So if we're able to plug that number in and it exists, the limit as x approaches this number exists, and basically just can you solve for the limit of it and see it exists. And if the limit at that number and the answer at that number are equal to one another, that function is continuous at that number. So continuous basically just means there's no splits in any way. So this would be a continuous line because there's no split in the line. Now it's not continuous because I just drew a hole in the line. So same can be applied with functions, but just in a more mathematical way. So there's three types of discontinuity, basically just things that make it not continuous anymore. So I'm going to bring this up closer to you so you can see it. So this here is my example function. So a discontinuity is it goes to infinity. Basically, if it goes to infinity at any one point, ignoring this one and this one, because those just mean it continues in both those directions. So this one means it can't equal this point here, whatever this is here, because it approaches infinity and then will eventually approach an asymptote. So that means it splits there in some way. And we would call that a discontinuity due to infinity, which normally only happens when you have rational functions that denominators don't cancel. Hence this little nonsense I drew here just to keep track. So now the second kind is a hole. A hole is basically just when you have a hole. Like if your function looks like this on a graph and you have a hole there, that it can't equal out that hole. Um, of course, because I just literally showed a photo of it, I'm friggin' stupid. So that's a hole here. A hole is a form of discontinuity because it can't equal that. And you get a hole when you have a rational function where the denominators do cancel out, which means you can find the limit of it, but you can't find the value of it. For infinity, you can find the limit of it, but you can't find the value of it. So that means we're breaking one of these. So a jump here is you normally have when you have a piecewise function, where they equal different things. So they equal different things and also don't equal one another. So that would be called a jump. Um, and that's also a form of discontinuity because even though the function continues, it's not a continuous line. Now there are different kinds of jumps that you can see and when certain things would happen. Like for example, this exists here. You can plug the number in for whatever this number is at jump. But the limits from either side, the limit as x approaches z from any side does not exist. So that would mean, of course, they can't be equal to one another. Now there is an instance where if you have a piecewise function that goes like this, where they swap here, where it's like this side is as x is greater than some number, and then this side here is x is less than or equal to that number. Um, you can check to see if they check out because this number here would be a yes. They would both be equal to the same limit, and you can plug that number in. That is when you would see that. So now our final thing is an intermediate value theorem. Now, this one is, you'll hear it and hear that it sounds super complicated, but then realize it's completely common sense. So, what the intermediate value theorem states is if our function f of x is continuous, that means at any point b and at any point, or any point a and any point b, where a and b are not equal to one another, the function will equal f of a and f of b at those respective points. Now, that means that if a and b are not equal to one another and the function is continuous, there exists inside a and b a number c, where this number c is equal to w, which exists inside of a and b as well. So that means that if it is continuous and a and b are not equal to one another, there exists a c, where c spits out a value of the function that is in between the values for a and b. That's all it states. Now, the actual thing says if f of x is continuous along closed interval a to b, and w is a number between fa and fb, where fa is not equal to fb, then there exists a number c inside interval ab, where fc is equal to w. That's what I just said, except way more complicated and doesn't need to be that complicated. And I also use photos, which makes things a lot easier to understand. So now, intermediate value theorem is kind of just something that you can reference for continuity, but we're not really going to find things that make continuity that. So one more thing that I didn't have space to write on here is I'm going to bring up my notes for this as well. So if f and g are continuous at a and c is a constant, then the following are continuous. So basically, if functions f and function g are continuous at any number a, and c is a constant, that would only be used in number 3 there. Then the following are continuous. So basically, f plus g, f plus or minus g is continuous. F times g is continuous. C times f and c times g are continuous. And that just makes sense from the same stretch factor thing that we talked about last video. And then 4, f over g is continuous, assuming that g at that number that we're talking about is equal to, or is not equal to 0, because then we would get an infinite. So yeah, we would get an infinite. Okay. Now the next thing. Any polynomial is continuous over the interval that to that. So that means I can write any string of nonsense, ax to the b power, that then goes on and on and on until we find a final constant. No matter what I write here, it is always continuous. And that's just how polynomials work. It'll always be continuous, no matter what. Okay? Any rational function is continuous wherever it is defined. So that means if we have the rational function x plus 3 over x minus 1, where this is defined is at the interval negative infinity, comma 1, unincluded, union, always forget to draw that union, 1, comma infinity. So this is where it's defined. It's wherever x can exist. And what it basically says is that a rational function is continuous wherever it is defined. So that means if you're not including something that involves a 1, if you're not including an interval that involves a 1, so let's say, for instance, we're involving negative 8 to negative 6, or we're involving 2 to 100,000, because it doesn't involve this 1 here where there's a union where it can't equal, they are continuous at these 2 points. Okay? Now another rule is these things are always continuous within their domain, of course. So just like how we said with the rational function. Polynomials are always continuous. Trig functions are always continuous. Root functions are always continuous where they're defined, as long as it's not a negative inside the root. Inverse trig functions are continuous as long as they're inside the domain of those trig functions. Rational functions are continuous as long as there's no things that we just talked about in the previous thing. Exponential functions are always continuous, just straight up always continuous. Logarithmic functions are straight up always continuous unless you're trying to set it equal to, or unless you're trying to set what's inside of the log equal to 0, I think, where it just straight up can't equal 0. So as long as you stay within the domains of those things, it'll always check out and be continuous. So now let's talk a little bit more about some specifics. I think there's 2 more. So if f is continuous at b and limit g of x is equal to b at x approaches a, then limit x approaches a of the composite function is equal to b. That's very specific. So limit g of x is equal to b. So that means as x approaches a, g of x is equal to b. That makes sense. So let's just say anytime we see a g of, oh, please don't freeze on me. Anytime we see a g of x, we can replace it with a b. We just know that that's how that can work. Then limit x approaches a. That's the same thing we're doing over here. So that means we can replace g of x with b. So limit x approaches a as of the function f to b is equal to f to b. Duh. Okay. That didn't need to be that complicated wording. And now the final one. We have one more. If g is continuous at a and f is continuous at g of a, then the composite function f to g of x is continuous at a. Well, that's kind of just like the rule that we just saw. So g is continuous at a. I'm going to just do that to represent continuous. I don't know the actual sign for it. And then f is continuous at g of a, then f composite g of x is continuous at a. So duh, because f composite is equal to f g of x is composite. So if f g of x is equal to that, basically anytime we plug g in for that at a, that would be just like seeing this here, where we would have an a here. So f is continuous at a, f is continuous at g of a. So it would be basically the output of g. If x is continuous at the output of g and g is continuous, then it's equal to everything, or they're all continuous. So that's just like the last rule. You'll never really need to know those rules. Now, let's talk about these. They just make your life easier if you're debating whether or not something is continuous. So we have these problems now. So 1, x, no, I have so many whiteboards. X squared minus x minus 2, is it continuous at 2? Those are my at signs, by the way. So is it continuous at 2? So let's just see. Can we plug it in at 2? We have to test to see, does f of 2 exist? So 2 squared is 4, minus 2 is equal to 0. Okay? If you can plug it in, you can probably do the limit of it as well. So the limit of it at 2 is then going to be also 0. I'm just going to shorthand it by doing limit x to 2. And then are these equal? Yeah, they are equal. So it is continuous. So now we're going to do 2. So 2 says x squared minus x minus 2 all over x minus 2 at 2. So same kind of deal. X. So we can plug 2 in? No, we can't. So first of all, no, it's not continuous at 2. So because we can't plug it in, it's not continuous. And then we have to try to categorize what it is. Because right now this could either be an infinity or a whole, just depending on whether or not this cancels out. So let's see, does it? This simplifies down to x minus 2 over x plus 1. Yes, it'll cancel because there's an x minus 2 in the top and in the bottom, so it is. So that means that this is not continuous due to there being a whole. So that would be our answer. And now let's find the final one, or no, not final one, second to final one. This is a piecewise function, everybody grown. 4 minus x, for x is less than 1. And then x is greater than or equal to 1. So first of all, we can immediately determine whether or not there's continuity based on this stuff here. Because if we, instead of seeing x minus or x greater less than 1, see this, that means that it can't equal 1 at all. So it's not continuous. Now we don't have that there. So that means it could be continuous only if at 1 both of these are equal to one another. So let's try to solve for it. So now let's think for a minute, how can we solve this? Let's use these continuity rules. So 1x plus 2, can we plug it in at 1? Yes, we'd have to plug it in for this one. So we're going to go plug, just to classify that what we're doing is plugging. If we're plugging it in, it's 4 minus 1. So that would be 3. And now if we're going to try to find the limit from both sides, they have to be equal from both sides. So let's just find the limit as x approaches from the negative side, because from the positive side we know it's going to be 3 because we just plugged it in. So from the negative side we'll try to find the limit. So I'll go limit, and then see as we plug in 1 here for the limit, because we can do that because nothing stops us from plugging in 1 here. So 1 plus 1 is 2 for the limit from the left side. From the right side, it's 3. So that means our limit as f of x as x approaches 1 does not exist. So that means it's not continuous. Yeah, I wrote it out the whole time. I don't know why, but I just decided I wanted to. And then the reason why, because there's a split here, which means we have a jump. Okay. Now we have one more, and it's another piecewise. That's blue. For 1 over x minus 1 over 2 if x is greater than 1, or if x is not greater than 1. It's actually as x is not equal to 1. And then if x is equal to 1. Okay. I just wrote a really bad x is not equal to sign. So now let's try to see, can we plug it in? Yes, we can. X is equal, or this is actually at 1. I think I didn't specify last time. At 1. Yes, both of them were at 1. So x here. So let's plug in 1. Plug in 1, we get 2. So plug 2. Now let's find the limit from either side. So from either side, it's going to be equal to whatever this thing is here. So we're going to go limit and see, can we plug in this 1? No, we can't. It's a 0. Because if we plug it in, we get 1 over 0, which is undefined, which means the limit does not exist. So therefore, limit does not exist. And if this is undefined, that means as we get closer and closer to x, this whole fraction approaches infinity, because as x approaches 0, 1 over 1 over x, or at least in this case, it would be actually as x approaches 1, 1 over x minus 1 approaches infinity. Because as x approaches 1, you get a number that's smaller and smaller at the bottom. Dividing 1 by a number that gets smaller and smaller means that 1 gets bigger and bigger until it approaches infinity. Which means we have an infinity here, so that's undefined. So we get not because there's an infinity. Okay, there we go. You could also say it's because of a jump, but in this case, it's specifically an infinity. It's a jump from infinity back to 2, but I don't think that that's something that your teachers would like you to say. I think they would like you to say infinity. There you go. So that is continuity.